Wrong somewhere. Okay. So first we'll go with half adder and then full adder. I think that's all is there in week 5, and also I guess K map, which we don't cover in this K map or Carnot map, which we don't cover. And I think that's all the syllabus of week 5. Let me just check. Yeah, Boolean simplification. Or week 6, then week 7, we have sequential logics and latches and all. Yep, that's all. Okay, so let's go it. What half adder is? 2-bit addition, 2-bit addition. This is 3-bit addition basically. And why we use full adder, and full adder is the last thing which we use for addition. We can count n number of bits from this. So let's go with half adder. So half adder is basically the two inputs. So let's draw a truth table. So, or say a sketch diagram. This is say a half adder. The number A, the number B, and we get what? The sum and the carry. If we go with the table for this, then we'll see A, B, S, and carry. So I think everyone knows the bit addition and all. So 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 is sum is 0, carry is also 0. For 0, 1, sum is 1, carry is 0. 1, 0, sum is 1, carry is 0. 4, 1, 1, the sum is 0, carry is 1. Okay, just let me. So we are just adding it, nothing explicit. And if we write equations for s and carry, sum and carry, so you can just notice that this s sum is just XOR between these two things, 0 double 1 0. So sum can be written as XOR of a plus, oh, XOR of a and b, while carry is, if you notice, it is uh, like let's solve it using K-map, or it is basically A B, nothing else, just A B, because the last this thing is 1. Okay, so this will be A B directly. So we don't need anything else. That's all is K map. If we draw the diagram for this, and one and get here. Sorry for my drawing. This is sum. This is carry. This is A B, and also let's solve circuit here. This is XOR. This is, and so yeah, there we'll get our adder. But the issue with this thing is, suppose we are adding two numbers and like this 1 1 1 1 0 0 1 1, and once we add this, so for 1 1, like uh, let me remove this and add it here. Yeah. So for this thing it is fine. 0 1, you can just directly write it as 1. And even for 1 1 it's fine, because you can directly write this sum as 0, and carry you can carry over 1. But here comes the problem. You can't take over the carry here. You just have a two input in this half adder. That's why we use full adder, and that's where it came the implementation. So let's create it, full adder. So this is, here becomes the input of three variables A, B, and C, and again the sum and the carry. So let's design a truth table for this. That will be A, B, C. Let me write a carry. So 0, 0, 0, 0, 1, 0, 1, 0. Okay, now if we add these numbers, then the sum is 0 for this, carry is again 0, sum is 0, sum is 1, carry is 0, carry is 0 for this, and sum is 1. For 0 double 1, the sum is 0, carry is 1. For 1 double 0, sum is 1, carry is 0. For 101, again carry is 1, sum is 0. For 110, again carry is 1, sum is 0. For triple 1, the sum and carry both are 1 1. Okay, let's design. Let's write equations for this. So if we see, or better to just write them. So for sum, it is it is. Let's use K-map better. This is A, this is BC, and if we fill out the K-map 0 1 1 1 1 0, so for 0 0 1 and 0 1 0, so 0 0 1 and 0 1 0, we have one for sum, and in this and here 1 double 0 and triple 1. So 1 double 0 and triple 1. For these all values, we have 1 in the thing. So if we write equation for this, that will be A complement B complement C, because we don't make can't make any groups. Then the second one is A complement B C complement for this thing. For the third one, we can say A B C complement, and for the fourth one, which is this A B C. Okay, and if we notice, then we can see that this can be written as A complement BC plus BC complement plus A common in here, B complement C complement plus BC, and this is same as writing B XOR C. This is XOR plus A B XOR C to the complement. And this can this if we consider B XOR C as some variable x, then this whole thing can be written as A XOR x. Or let me write, so A complement x plus A x complement. This can be written as A XOR x, which if we again put the value of x here, so that will be A XOR B B XOR C. So this the equation of sum is this. And if we take same thing for query, or if we try to write similar thing for carry, let's do it. So for carry, if we again use the similar K map, 0 0 0 1 1 1 1 0 0 1. So for carry, 0 double 1 is 1, which is 0 double 1 is 1, and in the next line, double, these three are 1. So we can make three groups out of it, the first one, the second one, the third one. So let's again make it, let me use some different color. So these are the three groups. Let's write equation for them. So if we write for the first group, which is the vertical one, that will be A complement B C, plus if we write for the first horizontal group, that will be A and C. If we write for the third group, that will be A again as a common, and the third thing is, oh, second thing is 0 B. So this is the whole thing. Okay, and I think this is right if I'm not making any mistake. Let me just confirm them. I think there's some mistake which I have made for the first column here. There should not be three variables for this. In the first one, just a minute. So for the first thing, it will be just B and C and not that A complement. That is a typo here. So sorry for that. Yeah, pen. Okay. So this is a typo here. So this will be AC and BC and AB. So let's create a block diagram for these all. So we have an XOR and we'll give A B as input, which will give us A XOR B, and again an XOR, which will give us, and we can use a C here, this will give us A XOR B XOR C. And coming to that, the and so the this is sum basically. If we go to carry, then we can use a AND gate here, where we can add A and B. So this will give us A and B directly. So this is AB, and if you see, uh, so this is AB, this is AB, and if you can see it, like let me create some space here. AB, this is AB, and if we add AND gate here and sort add this is AB. This will, so what the upper one will give us, that will be A B complement plus B uh, A complement into C, because we are fitting C. So this is C A XOR B, and once we add a OR gate here, we can get our output. This is a OR gate. So if we try to solve and fix it, so that is A B complement C plus A complement B C plus AB from the bottom. So this and this will B. Here A will get removed from this, or let me write. So if we write AB as common, or just A as common in this, and write B complement C plus B from the first and third value, we can write this as A B complement B C plus B. This is from the laws of digital electronics. Plus A complement BC plus A complement BC. If we open this AC plus AB plus A complement BC, we can again write B as common in both of them, so that will be A plus A complement AC, that will be BA plus BC, and again AC from here. So this is the equation we can get for carry. Again, you can simplify it and use extra gate, but this is a simplified logic which can be there for ladder. Aruni, any doubts? Like this is half adder and full adder. No? Let's then week 5 is ends here. And if we see in week 7, so there is nothing related to digital. There's circuit versus something which you can try to run this computations or create this diagram on some dashboard. Okay, so let's jump on to week 6 directly, and week 6 and week 7 I don't know don't remember the exact content, but it's week 6 and weeks 7 and 8. ठीक है, अभी week 7 में the first thing we will learn is SR latch using NAND gate. So this is a NAND gate. Okay, sorry for my drawings. This is S, this is R, and this is a short circuit connection. Wow. This is Q, this is Q naught. We are implementing this SR latch using NAND gate. It can be implemented using NOR gate also. So let's create a truth table here. S R. So possible combinations for SR is again 0 0 0 1 1 0 and 1 1. Does not this create? Yeah, it will create a deadlock. We'll run this for sure. So let's try 0 1. So if this is like a there is one property of NAND gate. So it is A dot B to the whole complement. So suppose this is just an AND gate followed by a NOT gate. So in AND gate, we know if any one input is 0, eventually we'll get a 0, and the NOT of that is 1. So what we can derive out of this is, wait, some things, some weird things. Just give me a minute. Wow. ठीक है, this we all know कि yeah, see, and is a b. Okay, so if any one input is 0, and will directly give us 0, है ना? So the not of that is 1. So what we can say, if any one input is 0, we can say the output of NAND gate is 1 directly without even looking at the other input. So let's try with the first thing, which is 0 1. So for 1 we can't say what's the output. For the 0, for the above gate, we can say the output is 1. So that 1 will come here, and 1 and 1 for the NAND will output as 0. And we can again with 0 will go here and this thing. So for 0 1 we can say Q is 1. Q is 1. Okay, now let's try the other case. If we fed in 1 0, तो ऊपर वाले का तो हम नहीं बता सकते, बट फॉर नीचे वाला NAND गेट वी कैन से द आउटपुट ऑफ दिस इज 1, देन 1 विल ट्रैवल हेयर, एंड 1 1 जब NAND गेट में जाएगा तो आउटपुट 0 आएगा, या सो दिस इज 0. And regarding the 1 1 thing, so let's say if we fed 1 1, we don't know what's the output of any other case, but this will be like q जो यहाँ जाएगा, यहाँ डायरेक्ट हम q पास कर रहे हैं, ठीक है, we are passing direct q here. So if q is a 0, we'll get 1 here, ठीक है, and if q is a 1, and 1 becomes 1, and not of that becomes 0. So if q is 1, we are getting 0. If q is 0, we are getting 1. That is the complement of q. So we can like confirm by this. So here we'll get a complement of like not a complement, but what is being stored in the last. जो पहले था वही hold हो जाएगा, ये hold state है. Now we can also confirm this by traversing the QA. So यहाँ से QA यहाँ जाएगा, that's Q complement. So if we see 1 के साथ अगर Q complement जाएगा, so if the value of Q is 0, so Q complement is 1. If the value of Q complement is 1, the output will be 0 because of the NAND thing. If the Q complement is 0, the output will be 1. So that is basically the whole state. So last state में था वही होगा. We don't get any new thing. And for the 0 0 case, this is invalid case. Why? Because if 0 goes here, 0 goes here, we know if NAND gates में अगर एक भी input 0 आएगा, अभी जिस पता है, then output is 1. So this is 1 and this is 1, which is contradictory because Q and Q complement can't be same. And even if we traverse it further, so 1 goes here, the output will be 1. And if 1 goes here, so if any one input is 0, output will be 1. So for both of the case, this is invalid. Okay. So this case is invalid. That's why this is like I issue an SR latch. This is fixed on later with some JK and SR latch, JK flip flop, but yeah, it is there. Now let's just move on to SR flip flop. So what we have drawn now is this AND gate, something, AND gate, output, this is input, this is input, this is a short circuit. Okay. So this is Q complement. Okay. Now this is SR latch जो हमने अभी तक बनाई थी. अभी इसको SR flip flop में convert करने के लिए we will just add a AND gate here. This is S, this is R, and we also have like a clock in between. So if let's create a truth table for this clock as R Q. So if the clock is 0, so this will output as 1 and this will output as 1. And for 1 1 we know that it will be a hold state for SR latch. Okay. So it doesn't matter what the S is, what the R is, but eventually the output is 1 1 here. So Q will hold. So this will be a hold state for it. So जो last में था वही will take care. So this is Qn plus 1. Okay. And even if we don't use Qn plus 1, Q Okay, so now if the clock is 1, we have four combinations again: 0 0 0 1 1 0 1 1. So let's try and all those. So if we give 0 0 as input, we'll know the output is 1 1. And from 1 1 we can say this is a hold state. So जो था वही रहेगा, that is a hold state. Let's try adding some other inputs. So, so if we fed 0 and 1, so this is 1, and since clock is also 1, so this is 0, and for 1 0 we know the output is 0. Similar, let's go with the other case, which is 1 0. So this is 1 and this is 0, and for 0 1 we can see here it is 1, so it is 1. And for, let's go with the last case, which is 1 1 again. So the clock is, this will be 0 0, since the clock is 1 and these inputs are 1. So for 0 0, note that this is an invalid state in SR latch. So again, it will be invalid here also. We don't know what will come in the output. Like whoever travel, like, so for, like, what's the logic behind this is, so this is NAND gate. So maybe this NAND gate has a propagation delay of 2 nanosecond and this has 3 or 4. So whichever travels first will get the output. Like something like this happens. You would remember that exactly. Okay. And the excitation table, like there is also a characteristic table for this. So if I draw that, or let me directly go with the excitation one. Should I draw the characteristic table also for SR flip flop? That is basically we need the truth table. From that we can create the characteristic table, and from that we can create the excitation table. So if you don't remember the excitation table, you can create from there. Okay, let me create that one also. So characteristic table for SR flip flop. So input is S R Qn Qn plus 1. So again 0 0 0 0 1 1 1 1 0 0 1 1 0 0 1 1 0 1 0 1 0 1. अब ये ticket table is, you can say, simply a larger version of this. We can just say कि हमारा आउटपुट क्या आएगा. So if it is SR is 0 0, we know on SR is 0 0, it will just show the output of the previous state. So this output will show, like, propagate directly in the here. Okay, for 0 0. Now for 0 1 we know, for 0 1 we know we don't care about the input, the output is 0. We don't know what's the input and we don't even care about it in SR flip flop. The output is 0. So for these two columns, it is 0 0. And if we go on the next level, and we can see this is 1 0. And for 1 0, the output is 1. We don't care what is the QN or the past state. So this is 1 1. And for 1 1, we can see this is an invalid state for here. So it is again be invalid and we don't care about those things. So that is, this is the characteristic table of this. So ये basically हमको ये बताती है SR and QN ऐसा क्या रहेगा, so that we can get Q, or like these are the previous entries in the machine and what will get the output based on this. Now let's create the excitation table for this. Excitation table for SR. Oh, not sorry. Yeah, SR flip flop. So that is Q1, Q1 plus 1. These are the inputs in this case. S and R. So ये क्या बताता है? This will basically help us in solving those questions जिसमें वो होता है ना कि हमारा इनपुट पहले 0 0 रहेगा, फिर उसको 0 1 पे जाना है, फिर वापस उसको 0 0 पे आना चाहिए, then it should go to 1 0. So and then it will again go here. So it will basically try to build cycles, runs in a loop. So this is because, so this is excitation table is helpful for there. So now how to derive the excitation table? So we can see input is 0 0 here. We want Qn plus to 0 0. So 0 0 is here, 0 0 is here, and that's all. So इसके corresponding हम S और R की entry देखेंगे. We can see 0 is same, but R is different. So that solely is depending on the, so we can write S is 0 and R as cross. Okay. Now if we go and see for 0 and 1, so where is 0 1? Here is 0 1. That's it. So we can directly write SR as 1 and 0. 1 and 0. Now again 1 0. So 1 0 is here. That's all we can see. 0 1, 0 1. And again for 1 1, we can see just one entry. Or not even, yeah, this is 1 1 and this is 1 in two entries. So we can see 0 is same, but this S is changing. So yeah, X and O. So you can see a pattern here. Just anything goes down, and they are just reciprocate or like reverse version of this. So X goes here, 0 goes here, 1 goes here, and 0 goes here. So you can remember any one of them and write the other. Okay, let's go to the next topic, which is D-latch. So let's go D-latch. So D-latch, as the name says, it's a direct kind of latch. जो input जाएगा वही output आएगा. And D-latch is in basically you can consider that D-latch as this thing. And let me find a diagram for that. For D-latch, I could not find a diagram. I think D and D-latch and D flip-flop are same in terms of diagram. I could not find a difference. If I made making mistake, I don't know. So D-latch and D flip-flop are almost same. Right? In terms of diagram, they are same. In terms of other things, they are same. Okay. So let's create diagram. So this is an AND gate, an AND gate. Again, this NAND goes in another NAND. This NAND. Again, these are short circuit connections. Q and Q complement. These are short circuit connections. Again, an AND here. And what we have is we just have an enable line here, enable line, and a complemented thing of this. So this is D. So here this is D and this is D complement, which is fed into this. ठीक है. अभी इसमें क्या होगा, इसमें बेसिकली हम जो इनपुट देते हैं वही आउटपुट आता है. इट डजंट मैटर व्हाट्स द लास्ट स्टेट इज. सो अगर हम इसका ट्रुथ टेबल भी बनाएंगे, so that is this. So 0 and 1, we don't care about the previous state. Whatever goes in, that goes out. Let's try even it. So here Let's suppose if we put a 0 here and this is 1, and enable line is again, if enable line is 0, nothing gonna work. If enable line is 0, that gonna hold the last state because you don't know input name. So if enable is 1, considering the case enable is 1, so this is also 1. So जिसमें ये 0 जाएगा, so output is 1, and 1 1 will become 0 here. And for 1 0, we know the output of SR latch. We come back here. For 1 0, the output is 0. So we can go here, there again. So we can see for 1 0, the output is 0. So if we have added 0, then the output is 0. Now let's try feeding 1 in here, 1 here. So 1, this is 1. So this will become 1, this will become 0. For 0 1, we can see for 0 1, the output is 1. So we can go back again. So we can say for 0 1, output is 1. Output is 1. And we have fed 1 here. So that is the output. That's why this is considered as a direct like kind of latch. Like output is basically equal to whatever fed in our input. Okay, then we have just JK flip flop remaining, and again the master slave JK flip flop. So let's go with JK flip flop. I need it. We are basically doing the revision of last weeks, like week 5 to 7, like 5 to 8.
Ah, okay, great. So, are you discussing concept or are you doing the assignment also?
We are doing just the concepts.
Okay.
Yeah. So for JK flip flop, that is, let me draw it. So again, every flip flop have this SR latch in there. This is Qn, this is Qn complement. This NAND gate, this we write J, this we write K, and again a clock pulse. So this is same as SR. Now what's the difference in JK is we just take this output and attach it here, and same for here. We add it in the NAND gates. So this is a 3 input NAND gate. Okay, so this is our JK flip flop, and the main difference is just to overcome that invalid state problem. So if we go with the truth table for this, so that will be J, K, Q, N. Again, if the clock is 0, nothing gonna work. So every time it's the previous state hold. Q1 plus 1. So Jn is 0, 0, 1, 1, 0, 1, 0, 1. And we can, let's ignore this one. Let's create Q1 plus 1 directly. Okay. So let's go with these inputs. So if we fed 0 0 here, 0 0, so the output will be 1 1 1 here. And from SR latch we know that 1 1 is a hold state. If we go up again, yeah, SR latch is the 1 1 hold states, the whatever the previous in memory, whatever the q is in the memory, it will get as the output. So this will be Qn. Okay. Now if we fed in 0 and 1, so this will become 1 and this will become 0. So for 1 0, we all also have seen that for 1 0 it is 0. So yeah, this is 0. And for again similar case for 1 0. So if we write 1 0 here, this will become 1, this will become 0. For 0 1, the output is 1. You can see that in the SR latch. Now what's the different in this is this 1 1 case. So if you write a 1 and 1 here, so both will become 0 0. Now for 0 0, we have seen in SR latch that this is invalid state, but it will toggle here. So let's run this. Mm, this is 1, this is 1, this is 0, this is 0. Wait, am I missing something? Yeah, so let me just do one thing here. It's like this, Q1 and again Q1 plus 1. So this is Q1, 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 0, 1. Now if this is 0 and if this is 1, so these two inputs are 1 here. J is 1, K is 1, the clock is also 1 at all the times. So the Qn complement will go here. So assuming that Qn is 0, so Qn will go here and it will travel till here. So once any zeros go inside the NAND gate, the output is 1 always. So we will get a 1 here. So consider this is 0, this is 1, we'll get output here as 1. And same for this the above thing, all of these three inputs are 1, so we'll get a 0 here. And for 0 1, we know from SR latch that the output for 0 1 is 1. So it will be a 1 here. Now if we write like keep the Qn as 1, so Qn complement will become 0. Now we try to fed in, so the Qn comp this input will become 0, like one of the inputs will become 0, and this will output as 1 and this will be 0. So this is 1, this is 0. And from SR latch again we can see 1 0, once we fed 1 0 in here, the output is 0. So yeah, that's it. So it's basically toggling like whatever the input is. So for 1 1, whatever the QN is, it will get toggled. Just this thing you have to remember. And if we write the characteristic table for SR JK flip flop, let me create it. Characteristics table of JK flip flop. So that is gonna be mhm, J K Q N, and also Q1 plus 1 0 0. So we can see if J and K are 0, 0, then it will work as the hold state, and whatever the input is, or whatever the last state is, it will be the output. So this will propagate here. And for 0, 1, we don't care about whatever the QN is, the output is always 0. So for 0, 1, it is 0, 0, and same for 1, 0, we don't care about what's the last state is, the output is always 1. Just the case changes here. For 1, 1, we can see whatever the input is, it will toggle. So this will be a 1 and this will be a 0 here. This is what's different from SR flip flop. And let me create the excitation table for this. So that is Qn plus 1, S and R, 0, 0, 0, 1, 0, 1, 1. So for 0, 0, you can see this second entry. Yeah, these two entries. So that will be 0. Same here. K will become X. Oh, sorry. JK. So this is 0 and X. For 0, 1. So for 0, 1, this is one entry and this is the other entry. So the J is 1 and K will become X. J is 1, K will become X. For 1, 0, this is 1, 0. So for this, and yeah, this is 1, 0 and this is 1, 0. So for this, we have two entries 0, 1 and 1, 1. So 1 is common in the K. So J will become as don't care and K will become 1. And for the 1, 1 case, which is this and this, the K is 0 and J is don't care. So this is the excitation table for JK. And here the week it ends. Again, the master slave JK flip flop is there, which is remaining. Should I cover that also? But I just have the clock diagram for that. Or should I end it here? That's all. I don't think so. There is any question I've seen regarding the master slave JK flip flop in the PYQs. Yeah, yeah, possibly. Right. Hmm. Okay, here the revision ends. Any questions or any doubts or something? No. Okay, let's end the session.